Hello everyone. Today we are going to start the chapter 1. So the title of the chapter 1 is The Dawn of the Quantum Chemistry. So I really like this book because this book shows the most important concept in the title, and by looking at the list of the sub chapters you can understand and follow the logics in this book, how the authors developed the quantum idea. So the early 20th century marked a dramatic turning point in the history of physics and chemistry. So classical mechanics represented by Newton equation, and electromagnetism had achieved great success in explaining planetary motion, thermodynamics, and the propagation of light. Yet a series of puzzling experimental results revealed deep inconsistency that classical physics could not resolve. So this chapter traces the dawn of the quantum theory, beginning with the problem of black body radiation, which led Planck to propose the revolutionary idea that energy is quantized. So Planck, quantization. We then move to Einstein's explanation of the photoelectric effect, which provided the first evidence for the particle nature of light. The quantization of atomic vibrations in solid explained why heat capacity deviate from classical prediction at low temperatures. So vibration of atoms in crystal, and the discrete spectral lines of hydrogen atom, H atom, discrete spectral line, first captured by Balmer and generalized by Rydberg, pointed toward the existence of quantized atomic energy levels. So building on these experimental puzzles, new concepts emerged. So quantized angular momentum, and de Broglie waves, and the uncertainty principle, each overturning classical intuition and establishing the foundation of quantum mechanics and quantum chemistry. So by the end of this chapter, you will appreciate how a collection of experimental anomalies forced physicists and chemists to abandon the classical worldview and embrace a new theoretical framework, one that fundamentally reshaped our understanding of matter, energy, and the microscopic world. So let's move on to the next page. Let us start the 1.1 session. The title is The title of the section 1.1 is Blackbody radiation could not be explained by classical physics. Let's see why the classical physics failed for the explaining the blackbody radiation. So the most important and the most well-known failure of the classical physics is the blackbody radiation. So the black body is an idealized object that absorbs all incoming radiation and re-emits its energy across all frequency. So if you have a body like this, so this absorbs all incoming radiation. Because the color is black, it absorbs all light and re-emits its energy across all frequency, like green, blue, red. So when such a body is heated, its color changes with temperature. So as the temperature increases, the color changes from red, progressing through white, and eventually shifting to blues as the frequency of the emitted radiation increases. So frequency nu increases. So this temperature dependence of radiation emission is a hallmark of the blackbody behavior. So in your textbook, the plot in figure 1.1 illustrates how the intensity of blackbody radiation varies with the frequency for the 3 different temperatures. So frequency of the emitted light is the x-axis and the intensity is the y-axis. So for the low temperature, like T1, the spectrum of the emitted light should look like this. Increase the temperature will change the distribution like this, and increase a little bit more, give the distribution like this. So as the temperature rises, the 2 key features are observed. The first is the position of the peak. The peak of the radiation curve shifts toward the higher frequency, so as you can see here. And the second point is the total emitted energy increases significantly, which means the energy intensity, right? So for the lower temperature, intensity is only this amount, but at the high temperature, you will observe the much higher intensity. So these systematic shifts are consistent with experimental observation, yet classical physics initially failed to account for them. So classical prediction is embodied in the Lagrange's law. Which describes the energy density of radiation as proportional to the temperature and the square of the frequency. t and the square of the frequency. So we are not going to derive the intensity expression suggested by Rayleigh jeans, but I will leave that as the homework for you, so you can derive the Rayleigh jeans expression. But we just write down their final result here. So their expression is the small change in the intensity law, which is the function of the frequency nu and the temperature. We can envision that at a certain temperature, the frequency, the intensity at the certain frequency is the independent of the frequency. So we can take that the intensity from this differential notation, and their final result is like this. So here the Kb, this is the Boltzmann constant, and C is the obviously the speed of the light. C, speed of light. And law nu T multiplied by d nu is the radiant energy density in the frequency range between nu and nu plus d nu. Okay, so while this law matches experimental data at low frequency, so at the low frequency, the intensity increases as the function of a square of the frequency. So it predicts that the energy density grows without bound as frequency increases, because you have only the square of the frequency term, so there is no bound for the high frequency region. So classical prediction, the Rayleigh jeans law prediction, shows that something curved like this. So this is RJ prediction. So you can easily find out that the divergence at the higher frequency region, somewhere like here. So experimental result shows that the radiation intensity should decay at higher frequency region, but classical physics predicts that the intensity should grow and should diverge at the higher frequency region. So this divergence, known as the ultraviolet catastrophe, So this obvious and glaring inconsistency between classical theory and experiment highlighted the inadequacy of classical physics and laid the foundation for the quantum revolution, beginning with the Planck's hypothesis of energy quantization. So let's move on to the next page. And section 1.2. The title of the section 1.2 is Planck used the quantum hypothesis to derive the blackbody law. So the failure of the Rayleigh-Jeans law originated from its implicit assumption the electronic oscillator responsible for radiation could possess any continuous energy levels as expected in classical mechanics. So in classical mechanics, so everyone recognized the energy as the continuous property. So the energy is continuous. So you can easily accept this argument. So if you think of the potential energy of some matter with the mass of m, then the potential energy of that matter should be m multiplied by gravitational acceleration constant and height h. So at here the g is constant and m is some given number. So the potential energy is the function of height. So EP is actually the function of height. So in the real world where we live in everyday our life, so h is continuous value, right? So you can place or you can throw the ball to any altitude you want. Like h can be 1 meter or 5 centimeter, even like if you have very accurate in throwing the ball, maybe some weird number like square root 2 centimeter, something like that. So h is basically the continuous. That means the energy level, potential energy, is also continuous. So the continuous energy is very well accepted by us because we live in the classical mechanics world. Under this assumption, the average energy per oscillator mode is computed by integrating over all possible energies. So we haven't discussed how to obtain the average quantity of some specific molecular property. I guess this will be handled in the advanced thermodynamic classes. But anyway, we can write down their final results. So if you want to calculate the average energy of some specific system, then you can add up all the possibility that energy has, like the probability as the function of the energy. And for the numerator, we are going to take the weighted sum actually. So energy multiplied by the probability of that certain energy. So in classical mechanics, it is well known that the probability is dependent on the Boltzmann factor. So probability is proportional to exponential minus energy over kBt. So if you do the integration using this analogy, this expression, then you will obtain the average energy as Boltzmann constant multiplied by temperature. So this is the reason why we meet the ultraviolet catastrophe at high frequency. So there is no limitation that the higher frequency region should not be occupied in the classical mechanics world. So to resolve this, Max Planck introduced a very radical new assumption in 1900. So I want to emphasize that this is just an assumption, a radical new assumption. So this is not based on any rigorous mathematical background or rigorous mathematical background. This is just from the Max Planck's intuition. So he hypothesized that the energy of an oscillator is not continuous but quantized, which means energy level is discrete. So we only have a discrete values proportional to the frequency. So the energy of the system should be given like this: N multiplied by h nu. So here h is the Planck's constant, one of the most important constant in the science, and the nu is the frequency. Okay, we can accept the Planck's constant because this is just a number, and the nu is the frequency. Okay, we know this quantity very well, but now we meet some weird parameter n. So Planck hypothesized that n should be 0, 1, 2, some like integer number. So like 0 and positive integer numbers. He thinks that n could not be a continuous energy, continuous number. There should be some discrete energy level in small atomic world. So this quantization drastically changes the average energy per mode and leads to a new distribution law for blackbody radiation, which is known as the Planck distribution. So the law ut is the up to here exactly same as the Rayleigh-Jeans law, but now we have the equation like so. Now we have two different function of frequency. So first part is nu cubic of frequency, and the second part is the exponential part. But the cubic of the frequency is in the numerator and the exponential part is in denominator. So there we can expect that their action should be cross-counted each other. So in his theory, this formula successfully explains the entire observed spectrum of blackbody radiation, matching experiments both at low frequency, which is explained by the cubic of frequency part, and at high frequency region, this exponential part in the denominator, this prevents the divergence as predicted classically. So this part assures that at the high frequency region, the whole value should decay to 0. So this Planck's hypothesis of energy quantization marked the birth of quantum theory, opening the path to modern physics. So, as I mentioned in the very early stage of this page, this is just assumption. So at the first time, nobody really liked this idea because there is no mathematical background. And this is just a sudden idea came up by Max Planck. Even though Max Planck was very famous and well-known physicist at that time, but no one really liked the radical assumption. So his idea was attacked by many physicists. But actually this theory is quite powerful because his blackbody distribution can explain the observed phenomena very well. And also many laws derived from the Planck's distribution supports this idea might be right. So let's take a look at 2 or 3 more examples, or not example, 3 laws derived from Planck's distribution. Let's move on to the next page. So far we have expressed blackbody radiation in terms of frequency. Since experimental data are often reported in terms of the wavelengths rather than frequency, so wavelengths is, we use the lambda for denoting wavelengths. So it is useful to rewrite the law accordingly. So using the relation between frequency, wavelengths, and the speed of light. So we can convert the frequency to wavelengths and wavelengths to frequency. So frequency is the speed of light divided by lambda, and d nu is given as minus c d lambda divided by lambda square. So Planck's law in wavelengths form should be given like this: d law lambda and t, nu law lambda t d lambda should be lambda to 5/5. HC lambda kBt minus 1 t lambda. So this expression gives the spectral energy density per unit wavelength interval, right? So there is no more frequency in this expression. We only have a variable as wavelengths. Okay, let's move on to the next page to check the Wien's displacement law. So an important consequence of Planck's distribution is that the wavelengths corresponding to the maximum of the radiation curve shifts with the temperature. You remember this experimental results? So at low temperature, the distribution of the energy density as a function of the frequency, something look like this. So at low temperature and high temperature. So we observe that, or maybe we can rewrite this one with lambda anyway. So we notice that the position of the peak changes according to the temperature. And this is summarized by the Bin's displacement law. So the lambda max multiplied by temperature is always constant, as the value of 2.90 multiplied by 10 to minus 3 meter and Kelvin temperature. So this means hotter body emits radiation with a peak at shorter wavelengths, right? Because if you have a higher temperature body, then to keep the multiplication of the lambda max and the temperature should be constant, the lambda max should be decreased, which means we are going to have the light with larger frequency. So the cooler bodies peak at longer wavelengths, right? So you might want to know how this magical number appear here. So if you want to find the lambda max, we can differentiate the law lambda, the Planck distribution given as the wavelengths. So we are going to differentiate the law lambda with respect to the lambda. So this is quite not really difficult job, so I will also leave this as the homework for you. So you can differentiate the Planck's distribution and let the first derivative to be 0. Then you can find the lambda value, specific lambda value that achieves the highest peak of the distribution. And you will realize that that value should be given as the temperature and the constant at here. Okay. Now let's move on to the next page to discuss Stefan Boltzmann law. I would like to discuss the relation between the energy density and the intensity. So energy density. So this is the amount of radiant energy stored in the radiation field per unit volume and per unit frequency interval. So power per unit volume and per unit frequency. So for blackbody radiation, the Planck's law gives like law nu is given as something like this. And intensity is a measure of the radiant power passing through a unit area in a specific direction and per unit solid angle and per unit frequency. So spectral radiance. So this is the called intensity. So what is the relation between the energy density and intensity? So this is important for the understanding Stefan-Boltzmann law. So I would like to discuss this relation. So energy density counts how much energy is present everywhere in space. So if you draw the picture like this, so energy density measures the energy in whole system, but intensity measures how much of that energy flows through a surface from a specific direction. So intensity is like we are measuring the flows from this black body, and we collect the flows of energy at this detector. So this is quite different, right? The energy density measures the total amount of energy stored in this system, but spectral radiance intensity is just the measures the flows from the black body at a certain space. So mathematical relation between these two quantities is that so the energy density is we can obtain the energy density by integrating the spectral radiance or the intensity over the all solid angles. So we will discuss this quantity later, and this should be divided by the speed of light. So as I mentioned, the energy density measures the total amount of energy stored in that system. So which means that we have to integrate the intensity over the all solid angles, which means we have to place this detector everywhere. Like we don't want to lose even single of the energy. So that means the solid angle integration should be something like this. So for the spherical coordinate, so we are going to integrate the something like this. So this will give you the 4 pi. So the relation between the density and the intensity should be 4 pi over c multiplied by intensity. So this will be important for understanding Stefan-Boltzmann law. Okay, let's move on to the next page. So now we are going to take a look at Stefan-Boltzmann law. So Stefan-Boltzmann law tells the total energy radiated per unit area per unit time from a perfect black body, and this is called the radiative flux R. So the radiative flux should be equal to C over 4 multiplied by EV, and the flux is also equal to the sigma, which is the Stepan-Boltzmann constant, multiplied by the temperature to the force. So here R is the radiative flux, and obviously the C is the speed of light, and EV is the total energy density integrated over all frequency, and sigma is Stepan Boltzmann constant. So we have very weird equality. So radiative flux is given as the total energy density multiplied by the speed of light divided by 4. So we want to derive this relation. So if you think of the black body on the polar coordinate, something like this, and the flux means that you are going to measure the energy flows out of from this black body. So your detector might be placed somewhere here. So this is the detector parallel to the XY plane, and they are on the G-axis. So that means you are not going to collect the emission flows out of from the opposite side of the detector. That means we are going to collect the radiation from this hemisphere. So the flux R can be derived by integrating the intensity over the frequency and the solid angle, accounting for the projection factor cosine theta. I will explain the projection factor later. I would like to integrate the intensity I nu to cosine theta d nu d omega, the solid angle, and we are going to integrate this quantity over this hemisphere. We already discussed that why we focus on the only half of the sphere. And let's try to understand the cosine theta. So if you think that there is some radiation like this, then they have some angle between G-axis. So we only collect the flaws parallel to the G-axis. That means we only need the cosine part of the radiation. So the projection factor cosine theta comes from that we are only collecting the radiation orthogonal or perpendicular to the detector plane. detector plane is here. So we want this component, right? So we can assume that the intensity is independent of the solid angle, so they are considered as isotropic. So we can factor out this integration for the frequency part and the solid angle part. Cosine theta d omega. So this is you already know this quantity. So d omega is equal to sine theta d phi. So integrating this part should be this one. So for the theta, we are not going to integrate for theta. We are not integrate up beyond the phi over 2, right? Because we only focus on hemisphere, so we don't need the theta beyond the pi over 2. So the integration range for the theta should be from 0 to pi over 2. And the pi or p, this one should be the angle between the x-axis. So the hemisphere covers the whole circle of p. So the integration range should be between 0 and 2 pi. So with this integration range, then this value results in pi. So now we have the value for this. This one should be equal to pi. So the radiative flux R equal to pi multiplied by the intensity integration over the whole range. So we don't really have to do this for now because we already know that the relation between the intensity and the energy density. So intensity is given as the energy density 4 pi C over 4 pi. So if we replace the intensity with the energy density, then this value should be C over 4, and now we are going to integrate the energy density. I'm very sorry, I was recording this video at home and my two kids, 4 years and 2 years old girl, they came back from the kindergarten and they realized that the daddy is at home, so they just opened the door and came into my room. Anyway, I'm very sorry. So with the intensity, so we can calculate the flux, and now we have the energy density, right? So if you integrate the energy density across the whole frequency, then this will gives you the total energy, right? EV here. So now you understand why we have such weird constant combination C over 4 in front of the total energy density. And the Stefan-Boltzmann law states that the total energy radiated, like the flux R, is proportional to the temperature to the force. So it is relatively easy to show that because we know the explicit expression for the energy density, the Planck's distribution. So you can plug in the Planck's distribution to this and integrate for the frequency. Then you will obtain, you will realize that the total energy should be proportional to temperature to the force. And actually this is the example 1-2 in our textbook. So you can do this by yourself. Okay, up to here we show that with the introduction of the radical hypothesis by Max Planck, that the energy is not continuous but rather quantized, or energy level is discrete, that resolve the ultraviolet catastrophe observed, like the predicted by classical physics in the black body radiation. And this radical assumption also results in two very useful law, the bin displacement law and Stefan-Boltzmann law, which is very well consistent with the experiment observation. So now we move on to the next section. Section 1.3. So we are going to discuss the photoelectric effect in this section. So the title is Einstein explained the photoelectric effect with a quantum hypothesis. So historically, in 1887, Hertz discovered that ultraviolet light shining on a metallic surface, so there is a metallic surface like this. So you shine the ultraviolet light. This could cause electrons to be ejected from the metal surface. So there are a number of electrons on the metal surface, and these electrons are ejected. This phenomena, called the photoelectric effect, could not be explained by the classical physics. So let's take a look at why classical physics failed to explain the photoelectric effect. So in the classical wave picture, electromagnetic radiation is described as an oscillating electric field, like this. You are very familiar with this diagram to illustrate the light. So electric field and magnetic field perpendicular to the electric field. So in this classical view, the intensity is proportional to the square of the wave's amplitude. So this is the amplitude, right? So according to this model, the higher intensity, which means the larger amplitude, should provide more energy to electrons, right? So classical physics claims that the energy is proportional to the amplitude squares. So if you have a higher amplitude, which means brighter light, this provides more energy than the kinetic energy of the ejected electrons should depend on the intensity of the incident light, right? So we have a energy conservation. You shine the light, so you provide the energy to the metal surface. Then some of the energy will be spent on removing electrons from the metal surface, and the remaining energy should be transformed to the kinetic energy of electrons. So the energy of incident light and the energy required to remove electrons and the energy of the kinetic energy of ejected electrons. So the sum of these two energies should be equal to the incident light's energy. So we can consider that the energy required to remove electron from the metal surface to be constant. This will be independent of the incident light intensity. In this case, if we increase the incident light energy using the brighter light with a higher amplitude, then we can expect that the kinetic energy of the ejected electron also should increase. But this is totally not true. So we are going to check the experimental observation. So we found two contradiction to classical physics. Contradiction to classical physics. So first is the kinetic energy independence of incident light intensity. So the kinetic energy of photoelectrons does not depend on the light intensity. Instead, intensity only affects the number of ejected electrons. So let's think of the example like this. So you have a red light. So the color is red, but the intensity does not mean the color, right? So if you have a really high power red light, then the color is very clear. So you have a strong red light, which means you have a high amplitude. You can also have a red light with a weak intensity. So regardless of the light intensity, whether strong or weak, the kinetic of the ejected electron is the same for the both case. Then what is the difference caused by using two different intensity? So the strong light ejects more electrons ejection compared to the weak red light. So this is contradicted to classical physics. And there is also very interesting observation. So there is threshold frequency. So below the certain minimum frequency, which is denoted as nu0, below this frequency, no electrons are ejected regardless of the intensity. So let's think of the example like 500 nanometer. So threshold frequency is 500 nanometer. So if you shine the light with the frequency 600 nanometer, despite the intensity, which means if you shine really bright light with the frequency of 600 nanometer, that could not eject the electron from the matter surface. So it's exactly contradicting to classical physics, because in the classical physics the energy levels are continuous. So in the energy level like this, so electrons in the matter surface is placed at somewhere here, arbitrary level. And let's think that matter surface. So let's think of this higher energy level as the free energy level, which means the electrons are ejected from the matter surface. So in classical physics, the energy levels are continuous, so there are infinite number of energy levels between the bound electrons and free electrons. So no matter the frequency of the incident light, it could be really small energy, but if you shine the light for a long time, or if you shine the light with very high intensity, then that cause the electrons could jump from the very lowest energy level to higher, a little bit higher energy level continuously. Then finally it could eject the electrons from the matter surface. That is the classical view of photoelectric effect. But this is totally not observed in the experiment. So if you shine the light with the frequency below the certain threshold frequency, it could not eject electrons at all. So if we summarize, if you shine the light with the frequency lower than the threshold frequency, no electrons are emitted. But if you shine the light with the frequency higher than the threshold frequency, electrons are emitted. And interestingly, the kinetic energy of the ejected electron increases linearly with frequency mu. So these results directly contradicted classical wave theory. So the Einstein found out that this is quite interesting, and to resolve this contradiction between classical physics and experiment observation, he used the quantum hypothesis. So let's move on to the not to the next page. Let's move to the down. So building on Planck's idea of quantized energy levels, Einstein proposed in 1905 that light itself consists of discrete energy packets, later called photons. So each photon has energy as h nu. So you all know that h is Planck constant and nu is the frequency. So Einstein considers the light as the packets of photons. So in classical mechanics, the light is illustrated something like this: electric field and magnetic field oscillating, something like this. But Einstein thinks that the light should be considered as the packets of some very, very small particles, which is called photons. And each photon carries the energy of h nu. So when a photon strikes a metal surface, it transfers its energy to a single electron. So it is very similar to the two balls. So there is ball here, and there is another ball coming. And this moving ball hit the stationary ball. Then the kinetic energy of this moving ball should be transferred to this stationary ball. So Einstein thinks the photoelectric effect something like this. So when the part of the photon energy is used to overcome the work function of the matter. So work function phi, this is the minimum energy required to remove electrons from the matter surface. And electrons, ejected electrons should have kinetic energy. And now we can write the energy conservation. So the energy of the photon h nu should be equal to the sum of the work function and the kinetic energy of the ejected electrons. So the kinetic energy of the ejected electrons should be given as the ha nu minus phi. So h is constant, and work function is also, this is a parameter for parameters, so this can be considered as a constant for the certain metal surface. So it is the characteristic of the metal surface. So for a given experiment, the P is also constant. So the kinetic energy is like a linear function of frequency nu. So if we draw the picture, so this is the frequency axis, and this is the kinetic energy y-axis. Then it looks like something like this. The slope is h, and the y-intercept should be minus phi. But we are not interested in the frequency below nu zero because there should be no electron ejection. So the kinetic energy should be 0, and above the threshold frequency we observe the linear dependency of kinetic energy on the frequency. So the existence of threshold frequency arises naturally because only photons with energy higher than phi can eject electrons. And increasing the light intensity only increases the number of photons, so hence the number of the ejected electrons, right? So the intensity is related to the number of the photons. It does not really have any connection with the energy of the photon itself. So this was the first direct evidence of the particle nature of light. So before the Einstein's photoelectric experiment, everyone thinks that the light as a classical wave. But with the quantum hypothesis of Einstein, now the light can be viewed or can be considered as the set of the particles which are called photons. So Einstein received the Nobel Prize in 1921 with his contribution to find that the light can be considered as the set of the particles. Okay, now we have understand that the energy level of the black body is also quantized, and the energy of the light also can be also quantized. So now we move on to the next section to see another example of energy quantization. Okay, section 1.4, the title is The Vibration of Atoms in Crystal are also quantized. So far we have observed a very non-chemical like a system. But now in atomic solid, the classical law of Dulong and Petit, this is very famous law, Dulong-Petit law, states that the molar heat capacity at constant volume, Cv, should be approximately 3 times R, where the R is the molar gas constant. You may learn this law in physical chemistry 1 or 2, when you learn the thermodynamics. So this prediction is consistent with experimental data at high temperature. So at high temperature, Cv is approximately equal to 3 times R. But as the temperature decreases, the heat capacity, Cv, is observed to fall below 3R and eventually 0 at very, very low temperatures. So at low T, Cv goes to 0. So if you draw the heat capacity at constant volume as a function of temperature, so it looks like something like this. So at high temperature, it converges to 3R, but there is some region the heat capacity is lower or smaller than 3 times R. So let's take a look at what happens here. So first, the motion in solids. So this is the atomic solid. Then solid means there is no free motion of its component. So there is no translation, and we are dealing with atom. So there is no rotation. So in gases, molecules can move freely contributing translation and rotational degree of freedom to the heat capacity. But atomic solid, that is not true. But the atoms are locked into the lattice sites by interatomic forces such as Coulomb repulsion, metallic bonds, or van der Waals attraction, etc. So the only type of motion available in atomic solid is vibration around its equilibrium lattice position. So if you think of the lattice something like this, so they have each atom should be placed in their equilibrium position, but they can vibrate, like they can slightly deviate from its equilibrium position. So this is called vibration. So each atom can oscillate in three directions: X, Y, and Z. And the vibrational degree of freedom contains both kinetic energy and potential energy term, right? So if you think of the ball connected to the spring, then it has its energy in terms of the kinetic energy and the potential energy terms. So according to the equipartition theorem, each quadratic term contributes half of kBt. So one vibrational degree of freedom contributes kBt because we have a kinetic energy contribution and a potential energy contribution. And now we have a 3 degree of freedom, and each degree of freedom contributes kBt to the heat capacity. That means heat capacity Cv should be equal to 3 kb per atom, or if you are dealing with mole, then there should be molar heat capacity should be 3R. But in quantum mechanics, the vibrational energy of atoms in crystal lattice is quantized. So each vibrational mode behaves like a quantum harmonic oscillator, which we are going to learn at chapter 4 or 5. But we already know the vibrational energy level of the quantum harmonic oscillator. Maybe you learned this already in the physical chemistry. So energy level of harmonic oscillator is V plus 1/2 and multiplied by HANU. And the energy interval in the vibrational motion should be the energy difference between the adjacent vibration energy levels should be HANU, because the transition between nu plus minus 1 is only available. So at high temperature, we can expect that the thermal motion energy kBt can be greater than HANU. So many vibrational modes are thermally excited, and we can expect the whole vibrational motion contributes to the heat capacity Cv. So we can expect that Cv becomes 3R. But at low temperature, The thermal energy is smaller than vibrational energy level interval. So that means the thermal energy is not sufficient to excite the vibrational energy levels. So very few oscillators can be excited to higher vibrational states, and most remain in their ground states. So that means not all the vibrational degree of freedom are available. So that means the heat capacity decreases sharply, and this heat capacity is smaller than 3R. And at the extreme case where the temperature goes to 0, all the thermal energy vanishes, so we are not able to excite the molecular vibrational energy level. That means there is no contribution of vibration, and the heat capacity becomes 0. Okay, so now we discussed that the energy level quantization occurs not only in the black body or the electrons energy, the light energy. And we also discussed that the vibrational energy levels are also discrete and quantized. So next move on to the hydrogen atom case. Section 1.5 is about the hydrogen atom spectrum. And the title says that the hydrogen atom spectrum consists of several lines. So one of the most striking pieces of evidence for the quantization of atomic energy levels comes from the line spectra of atoms. So when you apply a high voltage, then the electrons are ejected from the atoms, and you can record it the energy of the kinetic energy of the ejected electron, and you can calculate the energy level that the electrons were bound. So unlike a continuous spectrum, the emission spectra of atoms consist of only certain discrete frequencies. So if you see the figure in the textbook, so the first line of the hydrogen atom occurs 656 nanometer. The next one is 486 nanometer, and the next is 434 nanometer, and it becomes more crowded, and the distance between the adjacent peak becomes smaller and smaller, and now it converges to some specific value. So these discrete lines indicate that the electrons in atoms can occupy only specific energy levels. So that's why we observe these discrete energy levels. So we don't know the exact value yet, but the hydrogen atoms have a discrete energy levels, such here is the floor, second floor, third floor, something like that. So electron can only occupy the predetermined levels. So normally people observed some number like this. We think that this is quite random. If you observe the series of number like 1, 2, 4, 8, then you can expect that the next number will be 16, or 1, 3, 5, 7, then you can expect that the next number would be 9. But by observing 656, 486, 434, not really many people can discover there is some mathematical expression that can give these numbers. But the Johann Balmer, as far as I know, he didn't study chemistry at school. He just amateur chemist. So he discovered a simple mathematical relationship describing the frequency of the spectral lines in the visible and the near ultraviolet region. So here is his discovery. So frequencies can be calculated using this equation, 8.2202 multiplied by 10 to 14 multiplied by 1 minus n square 4 over n square hertz. So n could be 3, 4, 5, any integer greater than 2. So if you put the number, if you put the 3 to n and 4 to n and 5 to n, then this will gives you the, for n equal 3, this will gives you the lambda equals 656 nanometer. N equal 4 gives lambda of 486 nanometer. N equal 5 is lambda equal 434 nanometer. So 656 nanometer is red light, and 486 is like bluish green, and 484 is like bluish violet color, something like that. So this is empirical relation discovered by Balmer without any mathematical model and without any physical background. But this is the one of the most striking evidence of the electronic structure of the hydrogen atoms are quantized, or energy levels are discrete. We can reformulate the Balmer's expression in terms of wave number. So wave number, we denote the wave number using the V tilde, which is the 1 over lambda. So in terms of the wave number, the expression is 109,680 1 over 2 square minus 1 over n square in wave number unit. So this magical number is called Rydberg constant, and you will realize that this number can be exactly calculated from the Bohr model of the hydrogen atom. So I think we are going to meet the Bohr's model in the next lecture. So you can just feel that how the amateur's discovery can reshape the whole science. Okay, let's move on to the next page. Okay, the 1.6, this will be the last chapter, last subsection in this video. So 1.6, the title of the 1.6 section 1.6 is the Rydberg formula accounts for all the lines in the hydrogen atomic spectrum. So in the previous section we observed the Balmer's series. This covers the visible and near UV line. So Balmer's formula successfully described the visible spectra and near UV spectral lines of hydrogen atoms, but it was limited to the transition ending at the n equal 2 energy levels. So all the transition higher than 2, from higher than 2 to n equal 2 transition are explained by the Balmer's series. But the Lidberg generalized this expression to cover whole spectral range. So Lidberg formula. So the spectral line in terms of the wave number can be predicted with the Lidberg constant 1 over n1 square minus 1 over n2 square. So in this expression, n2 should be larger than n1. So that means that we are interested in the electronic transition from n2 to n1. And as already mentioned, this is the Lidberg constant, experimentally determined value as we have seen in the previous page. So this value is so the accuracy of the Lidberg formula was highly remarkable. It not only accounted for known lines, but also predicted spectral lines that had not yet been observed. However, in the late 19th century, no physical explanation for why this formula worked was unavailable. So it was only with Bohr's atomic model, which is proposed in 1913, that the Lidberg constant and the hydrogen spectrum gained a theoretical foundation, linking the observed spectra to quantized electron orbits. So in that moment, the experimental result is now understood by our humanity. So that's it for today, and thank you for your attention, and I will meet you on the next lecture. Thank you very much.